Hello everyone, today we're going to talk about mean squared as error estimation. The prerequisites are calculus, linear algebra, and probability. The goal is to analyze regression and linear regression from a probabilistic perspective. We're going to start with a very simple result, but as we will see, even though it's very simple, it's really useful and we'll use it in several places. The question here is, we're interested in estimating a quantity represented by a certain random variable y. And we will see later on that what we will do in regression is we estimate y from other quantities that we observe. But before doing that, let's consider a much simpler question where we have no data, but we do know the distribution of y, which we would estimate from maybe multiple observations of y. And we wonder what is the best estimate in terms of mean squared error. So here mean squared error is just we take the squared difference of the estimate and the quantity that we're interested in, and we perform an expectation. We need to use expectations to compute the error because we're modeling our quantity of interest y as a random variable, which therefore does not have a fixed value. So we have to compute the error with respect to its distribution, and a very natural way of doing it is taking the expectation of the squared error. Okay, so now the question is very simple. Because we know nothing about this random variable y and we are assuming we have no additional observations, we're going to just use a constant to estimate it. Okay, and here what we're saying is what is the best constant c that approximates y. If you want, if you imagine here the possible values of y and here the PDF of y, whatever it looks like, we want to find the best constant c. Okay, again, this would be the PDF of y. The best constant c such that when we look at the difference, okay, between c and all the possible observations of y, if we take the expected squared difference, that is minimized. Okay. So if we expand the expectation and we apply linearity of expectation, so here we're just expanding and now we're going to apply linearity of expectation, we end up with the following expression for the an equivalent expression to this for the expected squared error. And the important thing to note here is that once we have applied linearity of expectation, now this, the expected value of y and the expected value of the square of y, these are just fixed values. Okay, there's nothing random about it. Once you take the expectation, you obtain a deterministic value. So this means that we have a function that only depends on c. And now we can wonder, what does it look like? This function depends on c, and in particular, where is its minimum? This is a function in one dimension, so the natural thing to do is to just compute its derivative and second derivative. Okay, and if you remember your high school calculus, the derivative is equal to 2 times c minus the mean. Again, it's very important to stress that the mean and the mean square here, these are just constants. Okay, this is just a function of c. Once we have taken these expectations, there's nothing random about this, these are just deterministic constants. Okay, now we take another derivative and we end up with a constant second derivative. And basically, again, if you remember your high school calculus, this means that we have the following situation where this is c and this is g of c. Because the second derivative is always positive, this means that we have positive curvature. So it's going to basically look something like this. Okay, actually, let me try. I'm not very good at drawing, as you will realize. Okay, but we have something like that because the curvature is always positive. And the minimum here, for example, is going to be given by the point where the gradient is equal to 0. And that point is obviously E of y. So the gradient is 0 exactly at the mean. This is a very interesting result. It says that if we want to find the constant that best approximates a random variable in terms of mean squared error, that's exactly its mean. Okay, so we have that this function is convex with a minimum at exactly the mean. So the mean is the best constant estimate in terms of MSE. As we will see in a moment, this is extremely useful. It also means that if you have a lot of observations of a certain quantity and you want some kind of estimate for that quantity for a new observation that you do not have access to, and there's nothing else you have in order to estimate it, then the best thing to do is to average your historical observations, and that's going to be a reasonable estimate in the sense that it minimizes mean squared error. Okay, but what we're really interested here is in the regression problem, where we want to estimate some quantity of interest that we're going to call the response, and we do have access to some observed variables that are related somehow to this response, which we call features in machine learning, or in statistics they're also called covariates or independent variables. Like in this lecture, we're going to, or this video, to be more precise, we're going to model these quantities as random variables. So our response is going to be a univariate random variable y, and the features are going to be the entries of a random vector x. Okay, and now the question is, what function of x, when you have a function of features that estimate something in statistics and machine learning, we call it an estimator. What estimator of x is the best with respect to mean squared error? That's our question now. Okay, so just to be clear, we observe a specific value for the features, okay, which fixes the value of this random vector. And now, once we fix the value of that random vector, if you remember your probability theory, the uncertainty about y is captured by the conditional PDF or PMF conditioned on x having that specific value. Okay? That's what captures the uncertainty about y, and in particular it gives you the distribution of y. So now, if we want to minimize the mean squared error between y and x when we know that x has been fixed to that specific value, then this is the same as approximating a random variable w that has this distribution. Okay, that has the distribution that y has once we know that x has been fixed. It's exactly equivalent. But now we have reduced this problem of minimizing the MSE, okay, to a problem that looks exactly the same as before. We have a certain random variable, we're approximating it by a constant. Of course, this constant will depend on this particular value of x, but we're fixing it for now, okay? So the constant will depend on each value of x, but now we're fixing it to a particular value. And for that particular value, it is a constant. The solution to this we have just proved is the mean of the distribution of w, which is the conditional distribution of y given x. Okay, so this proves that the minimum MSE estimate is just the conditional mean. Okay, you fix. So here, by the way, we're using PDFs in this expression, but if y happened to have a discrete distribution conditioned on x, you would put a PMF there. Okay, the point is that if you want to approximate a random variable and you know the value of some other quantities, in terms of MSE, the best thing to do is just to compute the conditional average, conditioned on those other quantities. So here I have a picture of an example. Here our response is the rain in, I think, Oxford, if I'm not mistaken. Taken, I mean, over several years, and our feature is the maximum temperature. And now let's illustrate what I was saying up to now. Imagine that you know that the maximum temperature is equal to this value. Okay, then what you need to do is you take the conditional distribution, so basically a slice here. Ideally the slice, okay, would be like infinitely thin, so you would only take temperatures that had exactly that value, but of course that's not going to happen in the data. And basically we're going to take an average, use a different color, like an average over here, and that's going to be the best possible estimate for the rain in terms of MSE. The estimate is actually there. Okay, and this is exactly what I did for this data, and the red curve shows you the sample conditional mean. So that was the best MSE estimator if we assume that the data is allowing us to approximate the distribution very precisely, of course. Okay, so if we observed a value of 20, so then you would look at all the data points that are close here to 20, and you would compute the mean. Maybe it would be here. Okay, so this gives you a very, very reasonable way of estimating a quantity from another using MSE. You just use the conditional mean. And the proof is really, really simple. It follows from this result that tells you that if you want to approximate a random quantity, you should use its mean. Again, if you care about MSE, which is a very reasonable metric. So are we done here? Is this it? Like anytime we want to estimate a quantity from other quantities, all we need to do is compute the conditional mean? Well, yes and no. Yes, in the sense that that's optimal. So that would be great. No, in the following sense. So now imagine that instead of one feature, as in this example, we have 5 features. So apart from temperature, we also have pressure, maybe pressure at some other location, maybe wind intensity. 5 features, that's really not a lot. And we're going to discretize each to have like 100 possible values, okay? So now, if we are going to be able to estimate our quantity of interest, which again, remember is the rain, from these 5 features, how many conditional means do we need? Well, we need all the possible values that these 5 features may take. And all the possibilities is basically equal to, I always get these things wrong, but if I'm not mistaken, this would be 100 to the 5, right? If we had 2 features, one could have 100 values, the other one could have 100 variables. All the possibilities are 100 times 100. Now we have to do that 5 times. So this is basically equal to 10 to the 10, which is an insane amount of possibilities. We wouldn't be able to gather enough data to compute these conditional means from our training data. And this is only 5 features. In many situations, we have 100 features, 1,000 features, or even more. So we're not going to be able to systematically compute all these conditional averages from training data. This is just impossible. This is called the curse of dimensionality. Okay, and it's basically the motivation of why we need all these different machine learning and statistical techniques, because we're not able to just compute conditional averages. Because of the curse of dimensionality, we have to make an assumption when we are computing, when we are solving the regression problem. This maybe the simplest assumption, but a really powerful one, is that the relationship between the features and the response is linear, or rather affine. We'll talk about that in a moment, but you basically have that. The response is approximated by a linear combination of the features plus a constant that we call beta 0. Okay, and the assumption here is that if you fit this model in your training data, it's going to be for a fixed beta, so you're going to compute the constant vector of coefficients beta and the constant and this constant beta 0. And then you're going to be able to estimate this quantity well from like on your test data. This would be the assumption. Mathematically, essentially what we're saying is that the gradient of the regression function that connects the features to the response is constant. So here's a very simple picture. When you have just one feature and you want to estimate rain, note that in this particular case, because the slope of the linear regression function is constant, it's not able to realize that for higher temperatures, we tend to have less rain because the overall trend makes the line horizontal. Again, it seems like a great idea to have a nonlinear estimator here when you have one single feature. When you have many more features, it becomes much more difficult to fit nonlinear estimators, but it's still often a good idea. And there's several techniques to do that, such as kernel regression, nearest neighbors, or neural networks. Here we have another situation where the linear estimator, here we're estimating the minimum temperature from the maximum temperature within the same month. Here, the linear estimator is actually pretty reasonable. It does essentially the same as the nonlinear regression. Again, in multiple dimensions, instead of having a single line, because here we only have a single line because there's just one feature, we would have a hyperplane. Okay, and that would be, that's how the estimator looks like. So before we proceed further, let's deal with this constant term, which is a little bit of a pain when you're writing stuff out. Basically, it's just a constant offset. Okay, so if we go back here, basically beta 0, what it tells you is how much up you have to move the whole curve. So, you know, like something that we could consider is saying, okay, so how about I just go ahead and center this whole thing so that the axes are here, okay, by averaging the features and by taking the mean of the features and the mean of the response and subtracting them. Then I can fit the linear model and then I can shift it according to the mean again. Okay, this seems like a very reasonable thing to do to avoid having to include this constant shift in your model. And now we're going to see that that actually works. Okay, that's called centering. The idea is that we're going to, I don't particularly like this color, so I'm going to move to another one. I'm going to go back to green. Here we are going to say, okay, I'm going to center the response by subtracting its mean. I'm going to center the features by subtracting their mean. Now, can I just fit a linear regression model? And then afterwards, I can add back the mean of the response when I'm computing the estimate. Does that work? And again, it does work, and let's prove that it does. So first, let's determine what is the optimal value of this beta 0 in our linear model. Well, for any beta, it's going to be the beta 0 that minimizes this expression. Now, this expression, again, we see that our first result is extremely useful. This expression is the same as saying the expected value of W minus beta 0 squared, where W is just equal to Y minus xt beta, right? And we know that the solution to this, the value that approximates the constant value that approximates W better, is just the expected value of Y minus x transpose beta, okay? Because of this initial result that the mean is the best constant estimate. So now what we can do is we can just plug it back in to this expression. Okay, we can minimize over beta 0 and just plug the beta 0 that is always the best. Okay, and the beta 0 that is always the best is the expected value of y, this just by linearity of expectation. Okay, this is equal to this by linearity of expectation. And So we have plugged that in. Now that we plug that in, we can group terms, and we can realize that grouping terms, we have the centered version of y, and also the centered version of x, okay, because this is going to be minus x minus its mean transpose beta. Okay, so we can write this expression just in terms of, well, actually, let me leave that there. We can write this expression in terms of the centered versions of y and x. Okay. So this means that if we want to minimize this whole function in terms of beta and beta 0, what we can do is just minimize this other function that just takes into account the centered response and the centered features, and then beta 0 is just going to be equal to this. Okay, so we can add it up later. Okay, from this we would find the optimal beta, and then we would just add this constant term. Long story short, we don't need to worry about the constant term. From now on, we assume that everything is centered. In other words, that the response and the features are zero mean, because we can always subtract their mean. Okay. So in all our discussions about linear regression, we are going to assume that everything is zero mean. For this reason, we can just, if things are not zero mean, we'll just compute the mean from the data and center everything. Okay, so now we can get to our goal of minimizing the MSE for a linear estimator. Okay, so this is our cost function of interest. And now we're going to expand it and apply linearity of expectation. And this is what we get when we expand it and apply linearity of expectation. Again, as in the case when we were deriving the best constant estimate, once we apply expectations to things, then these things just become they become deterministic quantities once we have applied the expectation. And these deterministic quantities, for ease of notation, we're going to call them, well, this is the variance of y because we're assuming that y is centered, so its mean square is just equal to its variance. This is the cross covariance, which contains the covariance between y and each of the entries of x. And then we have the covariance matrix that contains the covariance between the entries of x. Okay? Because all of these things are deterministic quantities that at some point we will have to estimate from the data, here we have a function that is just a function of the constant vector beta that we want to estimate. And now, well, this just shows, in case you haven't come across a cross covariance before, it just contains the covariance between two vectors. Okay, the two vectors that are there. In this case, the response y and each of the features, which are the entries of the vector x. All right, so now it turns out that this function of interest, which is the MSE as a function of the coefficients that we want to find, is a quadratic function. Quadratic functions can have different shapes depending on the value. So here, basically, I've written this as a canonical quadratic function where this is a constant, this is a constant vector, and this is a constant matrix. And depending on the values of that, the constant c, the constant vector b, and the constant matrix a, the function will have different shapes. It could look like this if it turns out to be a convex quadratic function. It can look like this if it's a concave quadratic function, and it can look like this if it's concave in one direction and convex in the other direction. So it's very important for us to know how it looks like, because if it looks like this, for example, this would be really good news for us, because then this would mean that it would have a certain minimum, which would be our optimal beta. But if it looks like that, then you know, we wouldn't be able to find a minimum, or like this. Okay, so if you've you've studied a bit of multivariate calculus, essentially this boils down to whether the Hessian is positive definite. But we're going to just, we're going to derive that in a very simple way. So what we're going to do is we're going to look at the gradient and the Hessian, but mostly the gradient. And we're going to see here just by multivariate calculus that the gradient is equal to this, and the Hessian is just equal to the matrix A times 2. Remember that in our case of interest, the matrix A happens to be the covariance matrix of the features. Okay. So now the idea here is that the gradient determines a tangent plane to our function of interest. So in 1D, if I have a function like this, g of, oops, sorry for my terrible handwriting. So we have a function like that, g of beta. If you remember again your calculus, the gradient tells you, well, gives you a hyperplane. Well, this should be straight. Let me try again. Yeah, more or less like that. The gradient at this point, the gradient at this green point, determines what the tangent plane, okay, to the function. If we have a gradient that in 0, that tangent plane is going to be horizontal like this. And if the function is convex, then we have a minimum there. So we're going to focus on points where the gradient of this function is 0, and then we will see whether those are a minimum, or under what conditions those points are indeed going to be a minimum. In our case, the gradient is equal to 2a beta plus b, so we're going to be interested in points which we're going to call beta star, where this gradient is equal to 0. And we're going to rewrite the quadratic form in terms of those, in terms of that point where the gradient is equal to 0. Notice that if A is full rank, and we're going to assume that the covariance matrix is going to be full rank, then that there's a single point. So let's assume that there's a single point like that, and we're going to call it beta prime. And we're going to rewrite the quadratic form, setting B to be equal to minus 2a beta prime. This is just a reparametrization, it's exactly equivalent. Okay, it's just this change of variable. The point of all of this is that we're going to be able to derive a very simple solution under which, a very simple condition under which the minimum of the function is indeed at this beta prime. Okay, it's going to be useful to note that if we plug in beta prime and we look at what's the value of the quadratic function at beta prime, because here b is equal to minus 2a beta prime, the value of the cost function at beta prime is like this, minus beta prime transpose a beta prime plus c. Okay, that's the value at that point. Okay, so now let's go ahead and let's take the quadratic form and let's plug in the value of b that we have determined here. So again, we're going to take b and we're going to plug in beta prime in order to just express the cost function in terms of beta prime. That's our only goal. Okay, beta prime, by the way, here is just this constant that we obtain by setting the gradient to 0. So it's just a reparametrization of the quadratic form. Okay, so if we do that, we get this expression for the quadratic form. And now we can actually express this in a bit more of an intuitive way, like this. Okay, so here these are just algebraic manipulations. I encourage you to try to do this on your own. And there's this term that comes out so that we have the equality, but this is just exactly, if you remember, we derived this back here, this is exactly the value of the cost function at beta prime. So here what we have done is we have plugged in, we have done a change of variable here to write the cost function in terms of beta prime, and we discover that we can write the cost function as, by the way, this only works if A is symmetric. Okay, this derivation here. we have discovered that we can write the cost function in terms of two terms. One is just the cost function at beta prime, and another one is this, where we have the difference between beta and beta prime applied on the left and on the right of the matrix, which is essentially the Hessian of the quadratic form. So now, if for any possible difference, for any possible beta that is non-zero, this term this term is positive. I didn't mean for every possible value of beta that is not zero. For every possible value of beta that is not equal to beta prime, if this term is positive for any such value, then this must mean that the minimum of this function is this. Okay. So if for any non-zero v we have that this quantity v transpose av is positive, then this shows that beta prime, this point where the gradient is equal to 0, is actually the minimum of the quadratic function. This property is called being positive definite in mathematics, and it turns out that covariance matrices are positive definite because v transpose times the covariance times v is just equal to the variance of v transpose x. Okay, and variances are always non-negative. And in particular, if the covariance matrix is full rank, this thing is going to be strictly positive, okay? Because there's no zero variance in any direction. So basically, we have shown that if the covariance matrix of the features is full rank, then this quadratic form looks like this. And here, at the bottom of this bowl, is beta prime, which can be obtained by setting the gradient to 0. Now we're going to go back to our notation where we have covariances and cross covariances instead of A and B, and we set the gradient to 0, obtaining the coefficients for the best linear MSE estimator, which is the inverse of the covariance matrix, which we assume is full rank, otherwise this inverse would not exist, times the cross covariance. Okay. The corresponding MSE, because realize that the MSE estimator is these coefficients, is the inner product between the coefficients and the vector of features. The corresponding MSE attained by this estimator can be computed by just plugging it in like this. And again, here you just need to, I recommend that you actually work through this on your own. But basically all we're doing here is we're expanding the expression and then taking expectations everywhere. What we end up with is the variance of y minus a term that depends on the covariance and the cross covariance. Something interesting to realize is that the variance of y is essentially the error that you would get if you were estimating y from its mean. Right, because that's exactly the mean squared deviation from the mean. That's the definition of the variance. So this term is basically what we gain by using the features. Okay, it reduces. Using the features is going to reduce our error by that amount. This is what this second term means. Let's do an example where we have an additive model. Of course, this will never happen in practice, but it's very useful to analyze simple models that do follow the assumptions that we're making. So here we're going to assume that our response of interest is actually given by an inner product between the features and a certain vector of coefficients, and then there's some additive noise that is independent of the features that we don't have information about. We know we have information about x, about the features. This is what we observe, but we don't have any information about z. So now we know that the MSE is equal to the variance of y minus this term here, and we're going to derive what that term here looks like for the additive model. So let's compute the variance of y. These are two independent quantities, so the variance of their sum is just going to be equal to the sum of their variance. Okay, and when we split this out, we get basically something that is the variance of C plus something that depends on the covariance of X and its relationship with, and with beta true basically applied to the covariance of X. Then, if we look at the cross covariance, okay, this is the cross covariance between the features X and the response Y. Because X and Z are independent, that is going to disappear, and we end up with the covariance applied to beta true again. So when we plug this into here and this into here, what happens is that we end up with this expression where we get that the variance is equal to this and this term is equal to this. And it turns out that this term and these terms cancel because of this, because this is just the identity. And the MSE is exactly equal to the variance of the noise. And this makes a lot of sense because that is the component of the signal that we do not get to observe. It would basically be impossible to approximate Y to a higher precision than the variance of C because we know nothing about C. And only by observing X, it would be impossible to reduce the error below the variance of that unknown component. So this makes a lot of sense. Okay, so what have we learned here? We've learned that the mean is the best constant estimate in terms of MSE, and that result actually has allowed us to derive almost everything else. We have seen that the conditional mean is the best regression estimate in terms of MSE, but because of the curse of dimensionality, we often just cannot compute it. Because of that, we have to apply different assumptions when we're developing models, and a very popular assumption is linearity. And here we have seen that we can actually derive the best linear estimate only as a function of the covariance matrix of the features and the covariance between the features and the response. Thank you very much.